To efficiently solve phase relationship problems, you need to understand how different soil parameters are related. In this video, I will show you how to derive equations of different soil unit weights based on the basic soil parameters. This video will help you to understand the unit weight equations and hopefully help you to properly use all of these parameters in problems. In the previous video, we explained the basic parameters in soil mechanics, which are very important to understand the content of this video. So, if you haven't watched that video yet, please pause here, watch it, and then watch the rest of this video. But anyway, let's have a very quick recap of what we talked about. We introduced the phase diagram in soils, and we said it helps us to divide and present the three phases of a soil. It also helps us to better visualize the volumes and masses of these three phases. All the soil parameters that are listed on the left are defined based on these volumes and masses in the soil diagram. The void ratio is the ratio between the volume of void to the volume of solids. As you can see, none of these volumes have any limit. Both volume of solids and volume of void can be anywhere from 0 to a very large number. Therefore, the void ratio, that is usually expressed as a decimal, can be anywhere from 0 to a very large number. The porosity is the ratio of the volume of void to the total volume. And since the total volume is equal to the volume of void plus the volume of solids, the volume of void is always equal or smaller than the total volume. And as we just said, it is always equal or more than 0. So the porosity, that is usually expressed as a percentage, can be anywhere between 0 to 100%. The degree of saturation is the volume of water divided by the volume of void. And similarly, as the volume of void is the volume of water plus air, the volume of water is always smaller or equal to the volume of void. And when it's equal, the sample is fully saturated. This means that all the voids are filled with water. And the volume of water can be as small as 0, where the sample is called a dry sample. So the degree of saturation, that is usually expressed as a percentage, can be anywhere from 0 to 100%. So these three parameters were based on the volumes in a phase diagram. And the next one, the moisture content, is based on the weights or the masses. The moisture content is the ratio of the mass of water to the mass of solids. And since these two again are not related to each other, the moisture content, which is usually expressed as a percentage, can be anywhere from 0 to a very large number. The next parameter is based on both masses and volumes of a soil sample, and is called the density. The density is the ratio of the mass to the volume. And so far we have introduced three densities in a soil sample: the bulk density, the density of the solid particles, and the density of water, and this last one is a constant number. We have a parameter that is called the specific gravity in physics, which is the ratio of the density of any object to the density of water. In soil mechanics, we use this specific gravity for soil particles, for the solid particles, and we call it G sub S, which is the ratio of the density of solid particles to the density of water. And the last parameter that we have here is the soil unit weight, that is density times the gravitational acceleration, which is equal to soil weight divided by the soil volume. This is the very general equation for the soil unit weight that we all are familiar with from physics. But the purpose of this video is showing you how we can relate the soil unit weight to the other parameters in soils that we just introduced, because we have different types of soil unit weight, like the bulk unit weight, the dry unit weight, saturated unit weight, and so on. So in this video, as I said, I'm gonna be deriving these equations for these unit weights based on these parameters. And in the previous video, we also showed you how we can relate some of these parameters such as E, N, and these volumes. And lastly, this equation at the bottom, which relates the moisture content and the specific gravity on one side to the degree of saturation and the void ratio on the other side. I think this equation is the most important equation in phase relationships for soils. I'm going to be using this equation throughout this tutorial, but for those of you who are interested to know how this equation is driven, I will show you at the end of this video. The first density is the bulk density, and we all know the bulk density is the ratio of the total weight divided by the total volume, which can also be written as the volume of solids plus the volume of water divided by the total volume. But if we want to use these soil parameters on the left to get the bulk density, we can use these two equations that are actually equivalent. In the left equation, we have a specific gravity times 1 plus the moisture content in decimal divided by 1 plus E times the density of water. The right equation, on the other hand, is basically, as I said, equivalent to the left one, because the numerator of the left equation is specific gravity times 1 plus W, that is equal to specific gravity plus gravity times W. And as we showed in this famous equation that I'm asking you to memorize it, this can be replaced with this, and we can see that the numerator of the right equation is exactly the same thing. So we have two equations to find the bulk density, one based on the moisture content, the other one based on the degree of saturation. And in both of them, we have a specific gravity and the void ratio. So I'm gonna show you at the end of this video how to derive this equation. But in the rest of this video, I'm gonna use these two as the base to find the other unit weight equations. The next one is the dry unit weight. This unit weight quantifies how compacted the soil particles are in a soil sample. That's why this unit weight is widely used in compaction problems. A dry unit weight is a unit weight of a sample that has no water. So all the voids are filled with air. Therefore, the volume of water is equal to 0, as well as the mass of water. So when the volume of water is 0, we get the degree of saturation equal to 0. When the mass of water is equal to 0, we get the moisture content equal to 0. So going back to these bulk unit weight equations, when we have these two equal to 0, we will get this equation for the dry unit weight. The next unit weight is the saturated unit weight, that is defined for a sample that has no air in their voids. Therefore, the volume of voids are completely filled with water. So in this case, when these two are equal, their ratio is equal to 1. So the degree of saturation is equal to 1. So if we go to this right equation for the bulk density and replace the degree of saturation with 1, we will get this equation for the saturated unit weight. And the last one is the buoyant or the submerged unit weight of a soil. I'm going to create a separate tutorial for this unit weight and for the whole concept, but for now, let's just say the buoyant unit weight is the saturated unit weight minus the unit weight of water. And if we replace the saturated unit weight with the equation which we just introduced, for this we will get this equation. And now that we are familiar with these unit weights and their equations, it is going to be very useful to know the relationship between them. So the first one is dry to bulk unit weight. We know the bulk unit weight is equal to specific gravity times 1 plus the moisture content divided by 1 plus the void ratio times the unit weight of water. And we also know that the specific gravity divided by 1 plus A multiplied by the unit weight of water is the dry density. So we can easily get this equation that relates dry to bulk unit weight. The next is the relationship between the dry unit weight to the solid particles unit weight. The dry unit weight is equal to the weight of the solids divided by the total volume, and the solid particles unit weight is equal to the weight of the solids divided by the volume of the solids. If we solve this equation for the weight of the solids, we will get the unit weight of the solid particles multiplied by the volume of the solids. So if we go back to the first equation and we replace the weight of the solids with this, we will be left with dry unit weight on one side and gamma sub s v sub s divided by, now here the total volume can be replaced with the volume of the solids plus the volume of the voids. And now we can divide both numerator and the denominator with the volume of solids. And once we do that, we see that these two volume of the solids cancel each other out, as well as these two. And then here we have created the void ratio equation. And finally, if we simplify this, we will get this equation, that is the dry unit weight is equal to the solid particles unit weight divided by 1 plus void ratio. And the last equation is the equation between the dry unit weight and the saturated unit weight. From the equation of the saturated unit weight, we know that it is equal to specific gravity plus the void ratio divided by 1 plus void ratio times the unit weight of water. So if we divide the numerator of this equation, we will be left with this term plus this term. So we know that the first term is equal to the dry unit weight, and in the second term, E plus 1 plus E is equal to the porosity. So we can get this relationship between these two unit weights. So this slide summarizes everything that we talked about in these two videos, which is almost everything that you need to have and know to solve any phase relationship problems. And hopefully by now you're familiar with these basic soil parameters and are able to derive any other equation that is listed here based on them without memorizing anything, except these two equations. I'm going to ask you to memorize them because you need to know them to be able to get the other equations. And in the rest of this video, I'm going to show you how to derive them to better understand them. So let's go and see. So let's start with the first equation that I asked you to memorize. And before going through the derivation, let me just talk for a few seconds about the importance of the density in phase relationship problems. Density relates the volume to mass of any object. And in phase relationship problems, using the density, we can relate the volume of solids to the mass of solids, and also the volume of water to the mass of water. So knowing this, let's start with the moisture content equation. And we first need to solve it for the mass of water. Then we need to replace the masses with density times volume. Then we need to replace the volumes in this equation with equations that are based on the void ratio and the degree of saturation. And finally, once we get here, we need to replace these two densities with the specific gravity to get to our final equation. And finally, the bulk unit weight equation. But before going through the derivation, let me show you a very useful assumption that we can make for phase relationship problems. If no masses or volumes are given, you can assume either one volume or one mass. So in this case, we usually assume the volume of the solids to be equal to a unit volume. So by making this assumption and using the void ratio equation, we get the volume of the void is equal to E. And from the degree of saturation equation, we will get the volume of the water is equal to degree of saturation times E. So this is a very useful assumption that we can use in phase relationship problems to find the volumes and masses of a sample. So now let's just start with the bulk density equation that is equal to the total mass divided by the total volume. The total mass can be replaced with the mass of solids plus the mass of water. And the total volume can be replaced with the volume of solids plus the volume of voids. We just showed that the mass of solids can be replaced with the density of the solids times the volume of solids. And for the mass of water, we first use the moisture content equation to find its relationship with the mass of solids. Then in this equation, we replace the mass of solids with what we just talked about. Once we do these replacements, we get to this equation. And now it's the time to make our assumption, that is, the volume of solids is equal to 1. So if we replace these volume of solids with 1, and also the volume of void with E, and also factoring out these two density of solids, we can get here. And here, the density of the solids can be replaced with the specific gravity times the density of water. And then we will get to this equation for the bulk density. And if we multiply the densities in both sides of the equation with the gravitational acceleration, we get our final equation for the bulk unit weight. So this concludes this video. I hope you enjoyed it and learned everything that you needed to solve phase relationship problems. In the next video, I'm going to solve some example problems and show you some tricks to solve these problems.